was waiting for somebody to take a test at 8 this morning, and then they didn't show up. And I thought, well, I'll give them a couple more minutes, and then before you know it, I'm late to class. So I'll begin. With a word of prayer. So, well, Dearly Father, we thank you for this day. I thank you again for these students, for the pleasant weather outside, and I just thank you for all your many blessings to us this day. Pray that you guide our work, and again, just to encourage the students, if they're struggling, just to do their best, Lord, each day for your glory. In your name I pray, Lord Jesus. Amen. Okay, so today I'm talking about inverse functions to start with. And although before I can get to that, I actually have to talk about what are called one-to-one functions. Do you guys know what a one-to-one function is? So let me give you a definition. F is a one-to-one function if f of x1 equals to f of x2 implies that x1 is equal to x2. All right. We could also say this. F is not 1-to-1 if there exists x1 not equal to x2 such that f of x1 equals to f of x2. All right. So technically the sentence above, I should add, this is for all x1 and x2 in domain of the function. So this is a one-to-one function. All right. So let me give you an example of something. Let me start with an example of something that's not a one-to-one function. All right. So example of something that's not a one-to-one function. Oh man, I tricked myself into thinking I had a purple. It's not purple. Here we go. Example 1. You could have something like this. All right. If this is y equals f of x, all right, if this graph is the graph of y equals f of x, something like that, that function is not one-to-one. All right, the reason for that, we can see if we draw a line, a horizontal line here like this, all right? See this? Draw this horizontal line right here. And notice what happens. This horizontal line intersects the graph here and also here, right? So I can think of this as x1, and I can think of this over here as x2, right? And we have x1 not equal to x2, yet f of x1 equals to f of x2, right? So in this case, this graph fails the horizontal line test, is what we say. So this graph let me write in a different marker. That one's kind of hard to see. Fails the horizontal line test. Now, not every function has to pass the horizontal line test, right? This is the graph of a function, the red line, right? This red curve is the graph of a function, that's fine. It passes the vertical line test, right? Only cuts through, each vertical line only hits the graph at most one point, that's fine. It is a function, graph of a function, but it's not a one-to-one function, see, because there are two different inputs which give the same output. If you have two different inputs which give the same output, the function's not one-to-one. All right, so passing the horizontal line test, what that means is that no matter what horizontal line you draw on the graph on the xy plane, that horizontal line will only hit the graph of the function at most one point. So like an example where you do have a one-to-one function, we could have something like, I mean, there are many, many possibilities, but here's one. We'll do one of these guys here. Like the graph could look like, oh, for example, this here. Right, so I'm saying it's got a vertical asymptote and it's got a horizontal asymptote as pictured, right? I don't really care about the numbers so much. This function, y equals f of x, that's given. This would be a one-to-one function, right? Do you see the difference? I mean, I can start drawing in some horizontal lines for you. I'll do that. How about that? See? Here's one. Here's another. Here's another. Here's another. Here's another. Here's another. We could go all day, right? Each horizontal line that you draw, it only hits the graph in what? Just one point, right? Each one of these dots that I'm drawing represents the unique place on the graph where that y value is reached, right? And then, like, for example, you guys can make this whatever you want. Let's suppose that the horizontal asymptote's at 3, right? So there is the horizontal line at 3, and that just doesn't hit any point on the graph at all, right? And that's fine. Just like the vertical line test says, there's at most one point that you intersect with your graph if it's going to be the graph of the function. The horizontal line test says you can hit at most one point on the graph of the function, right? Okay, so graphically is one way we can detect the function being one-to-one. What's another way? Well, we can use the algebraic approach. So we can test for one-to-one algebraically. So let's call that example 3. Suppose we have f of x equals to 3x minus 8, all right? There's a function. The question is that function one-to-one? Let's test for it algebraically, all right? So what we're going to do is, you know, over here where I wrote x1 and x2, in practice, when I actually put this thing into practice, what I'll replace this with is f of a equal to f of b implies a equals to b, because that just makes the algebra easier to see. x1 and x2, I mean, you could use x1 and x2 if you want, but I just think a and b is easier to kind of just stare at. So what we're going to do is we're going to assume f of a is equal to f of b. And then our goal is to show that that assumption implies that a is equal to b. That will prove that the function's one-to-one. Okay, so what does f of a equal to f of b give you? For this function, it gives you 3a minus 8 equals to 3b minus 8, right? Then all you got to do is add 8 to both sides, right? 3a equals to 3b, right? Then divide both sides by 3. And we've got a equals to b. So thus, f is 1, 2, 1, right? And in retrospect, this is totally unsurprising. Why? What's the graph of this function look like anyway? You're like, I thought you were going to do it algebraically. I have done it algebraically. Let me circle back and talk about the graph here for a second. What's the graph of this function? It's a line. Very good. Its y-intercept is -8, right? And it's got a slope of 3, right? So roughly speaking, it's something kind of sort of like that, right? Does that pass the horizontal line test? Absolutely, right? Each horizontal line only crosses the graph just once. Let's do another algebraic one. Example 4, we could look at, for example, f of x equals to x to the 4th minus x squared. Oh, I'm sorry, that's too much. Let me just do like x to the 4th. Oh, fine. X to the 4th minus 1. There we go. Let's see if this function is 1 to 1. Let's try to do it algebraically. Let's see how that goes. So we assume f of a equals to f of b. All right, what does that give me? That gives me that a to the 4th minus 1 equals b to the 4th minus 1. And then what can I do? Add 1 to both sides, right? Okay. A to the 4th equals to b to the 4th. And now how can I solve that equation? How can I get rid of a 4th power? I can take a 4th root, right? So I can take the 4th root of both sides. What does that give us? See, we might be tempted to think of that, but it does not. Let me remind you. So here's the deal. The nth root of x to the n is equal to two things. It's equal to x if n odd. It's equal to the absolute value of x if n is even. So we have to be careful. When we're taking an even root of an even power, we actually get absolute value. So what this would really simplify most directly to is absolute value of a equals to absolute value of b. Which tells you what? It doesn't tell you a equals to b. That tells you that a is equal to plus or minus b, right? So we're going to have to say no. This one's not 1 to 1. Yeah.
Can't you already tell that by the formula?
Oh, not a parabola, but but you're right. You're right. Absolutely. We could take a graphical approach here. And graphical approach, right? And so this is equal to, I like that, x. So this is like x plus 1, x minus 1 times x squared plus 1 if you factor it, yeah? So it's got x-intercepts of like 1 and minus 1. And it's generally kind of opening up. The y-intercept is minus 1. So you're right, it's kind of like a parabola, but it's, it's more kind of more bullish. I don't know what's the right word for it. It's fatter than a parabola at the bottom. But yeah, you're right. So obviously it fails the horizontal line test. And so there's another thing we could say here. So yeah, this algebraic argument's okay, but there's a different way we could go here, right? Which would just be like a totally legitimate. So let me complete the thought here. 3 ways to see it. What I've written in red, all right? We could do that. The graph that I just drew, that also shows f is not 1 to 1. All right? Because that's the graph y equals f of x. And there is a third and even easier way, which is just to provide a counterexample. All right? I mean, all we have to, the second line here, right? To show it's not 1 to 1, all we have to do is to find a particular pair of numbers whose outputs give you equal, and yet they're not equal inputs, right? So here, there are a few different, there are many, many choices, as you can see from the graph, but a couple of obvious choices. So like a third way here would just be to go, well, f of 1 is equal to 1 to the 4th minus 1, which is equal to 0. F of minus 1 is equal to minus 1 to the 4th minus 1, which is equal to 0. Since 1 is not equal to minus 1, yet f of 1 equals to f of minus 1, we find f not 1, 2, 1. That is another way. And I would say, goodness gracious, excuse me. I would think that's the most efficient way for this. If it's a non-example, if it's not one-to-one, the easiest thing to do is to find a couple of points that you can plug into the function and get equal outputs, and yet they're not the same input. But if you don't know ahead of time if the function's one-to-one or not, well, the algebraic path, and you don't want to graph it because whatever reason, then the algebraic approach is you can try it. Algebra can be hard sometimes, right? Okay, so now you guys are experts at what a one-to-one function is, right? I mean, it's really not that deep. It's just it kind of doesn't turn back on itself essentially, right? That's most of it. It's got to either keep increasing or keep decreasing, I mean, it could also, like this one, we could have, you could have also, like for this example back here, you could have turned it over. Like you could have had it increasing here, and you could have turned this one over so it went down like that. So you could have had it increasing here and decreasing there. But if there's a place where it's increasing and there's a place where it's decreasing, there has to be some sort of like asymptote between the things. Otherwise, you're going to have a doubling back, which means you're going to fail the horizontal line test, like graphically. Yep.
Okay, moving back to example 4.
Mm-hmm.
Why is it at the very end it's the absolute value of A and B, but only B is specified?
Oh, just think about this. So the plus or minus of A and the plus or minus of B, they're like logically disconnected. So there's really, in principle, 4 different cases here. So like you could have A positive, B positive, which would mean you got plus, right? You'd have A equals B. If you have A negative but B positive, then you'd have minus A equals to B, which would still give you A is equal to minus B, moving the minus to the other side. If A was negative and B was negative, then you'd have minus A equals minus B from this equation, which would again give you A equals to B. So it's just like if you think through the 4 logical possibilities, they're all summarized in just putting a plus minus like that. I mean, the absolute value is forgiving to us in that way, right? Because it would be annoying if we actually had to keep track of four cases and stuff like that. But we're always doing this, whether you realize it or not. Like anytime we take the square root of an equation, we're really doing this. Like we take the square root of both sides. When you have something like, x minus 3 squared equal to, I don't know, 4, and you take the square root of both sides, right? I don't really advertise this much, but it is true. Like the most logically immediate step is that says the absolute value of x minus 3 is equal to, well, 2, right? And well, so here there's no variable, so there's kind of no ambiguity, right? Like it's square root of 4 is 2, so you can't see it as much here. But in principle, it's also present here. But I guess I need something like, to appreciate it more, I would need something like, I don't know, x plus 7 or something squared. Then you could kind of see it better. It would give you this. But then you can replace that logically with like x minus 3 is equal to like plus or minus the other side. But anyway, I'm getting into the weeds here. This is not helping us today. Let me get back on track here. Our time is precious in here, unfortunately. Oh, man. So, listen, one-to-one is a property we need for our function in order to find what's called the inverse of the function, all right? So let's actually start with an example, okay? So here I'm going to look at f of x equals to x cubed plus 2, and g of x equal to the cube root rather, of x minus 2. All right. And what we want to do here, and I just want us to get warmed back up on composition of functions, all right? So try composing both of those functions in both ways. Like do f composed with g and do g composed with f. See what you get. F composed with g of x means what? F of g of x. And I also want to calculate g composed with f of x, which would be g of f of x. So the way a notation I like to use in here is to think of that as like f of g. So I plug g in the formula in the place of x. So that would give me like g cubed plus 2, right? Which is really like the cube root of x minus 2 cubed plus 2, which is x minus 2 plus 2, which is, well, x. All right. And the other composition, I'd have g of f. What is that? The formula for g is the cube root of the input minus 2, right? So I do cube root of f minus 2. But that's the cube root of x cubed plus 2 minus 2, which is the cube root of x cubed, which is, well, x again. So this is kind of an interesting pattern, right? Oh well. So we'll keep this. Leave yourself a place to make a graph down here in your notes, okay? We're going to add a graph to that eventually. Example 6, a little bit different. So we'll do f of x equals x squared, let's say plus 3, and g of x equal to the square root of x minus 3, and see how that goes. Okay, pretty similar examples, but with a square root instead of a cube root. What happens? What's the difference here? Let's also calculate the composition of f with g. And so we'll have, f of g of x, which we can think of as f of g, which is g squared plus 3, which is the square root of x minus 3 squared plus 3. Sorry. You can't leave now. Now the square root squared is just the input again. So that's just x minus 3 plus 3, which gives us x. All right, so that calculation pretty much went the same, right? But this one, g composed with f, is going to go a little bit different. G composed with f of x is g of f of x, which is g of f, which in this case is the square root of x squared x squared plus 3 minus 3, which is the square root of x squared. And what did we just get done talking about? We just got done talking about how the square root of x squared, it's not x again, right? It's actually absolute value of x. See, there's an asymmetry here in these problems. All right. Okay, so again, leave yourself a little bit of space for a graph here. We're going to come back to these examples in just a minute or two. Probably shouldn't have done that. So what is an inverse function? How do we define an inverse function? All right, because actually what we're going to see is that example 5 actually is an example of inverse functions, all right? Whereas example 6, these functions are not quite inverses, all right? So let's talk about how that's defined. So here it is. First of all, I'm just going to draw kind of a schematic picture. And so here's this, I always draw this kind of abstract picture in any of my classes. You know, here's a set, let's call it U. All right. And then over here you've got some other set, V. All right. And you've got a point in here is like X, a point in here is like Y. All right. And there's a function that takes you, I can think of a function as a mapping from one set to another. It's some kind of assignment that transfers you from U to V. So I can think of F as sort of like this, all right? This is F. And then I can think of F inverse as going the other way. All right? So notation for this, well, we have a couple different things in this scenario, right? We have F of X is equal to Y, but if the inverse function undoes what the function does, then F inverse of Y is what? It's just equal to X again, right? And so here's a more systematic, with words kind of definition. If F from U to V is a 1-to-1 function, then F inverse is going from V to U is a function satisfying F inverse of Y equals to X whenever F of X is equal to Y. And oftentimes I decide whether or not a function is an inverse function or not by checking the following two things. So we need, number one, we need that F of F inverse of Y is equal to Y for each Y in V. And we need, number two, we need that F inverse of F of X is equal to X for each X in U. So I don't require you guys to like memorize this definition or even know it. What I require of you is you be able to work the problems I'm going to share with you, right? This definition is more abstract than we need in this course, let's say, but I state it because I think this is really what the definition is, and I think not stating it this way just kind of, it actually makes it more complicated to not do it this way. But anyway, listen, there's terminology to talk about here. Like, what is U and V in terms of domain and range? Do you remember? I mean, we could talk about that, right? So notice U, right? It's equal to the domain of F, right? But what else is it equal to? So it's the input for F. It's the output for the F inverse, right? So it's the domain for F. It's the range for the inverse function. And V, in this language, that's the range for F. but it's the domain for the inverse function. So there's this duality, this juxtaposition, if you will. Well, that's the wrong word. It's a mirroring, if you will. Domain of the function is the range of the inverse. The range of the function is the domain of the inverse. There always has to be this interplay, and that will help you decide whether or not you've done calculations correctly or not, all right? But at the start of all this, we're assuming what? Like, this is mission critical here. In order to find, like if I ask you, find the inverse function if possible, what's one of the things that you should immediately check on? There's pretty much one thing, right? This. Is it one-to-one, right? If it's a one-to-one function, you have hope of finding an inverse. If it's not, then you don't. Oh man. Well, I'm my worst cameraman. Look at this. Sad, sad, sad. Hey, you guys are here, right? So, sorry for the people who are not. Although they didn't really miss much over there, did they? I just drew this picture and said these words. But now, okay, so now look back. Let's look back at examples 5 and 6 now. So what does example 5 show you? Do you see what it shows you? So actually, this one right here, example 5, those are inverse functions, right? Look at it. They're satisfying the two equations which we need for it to be an inverse function, yeah? See that? So these two calculations right here, these tell me that G is equal to F inverse. And also, you do also get that F is equal to G inverse, if you want to look at it that way. Right? If two functions are inverses, then there is this relation as well. They're inverses for each other. What's the graph? What's this problem look like graphically? Can we do it? Can we graph the function and the inverse function on the same graph? I can foolishly try, right? So we've got a cubic function which is shifted up too, right? So that's something like this, right? Roughly speaking. I tried. Anyway, my simpler question to you, as you look at this red graph, is something pretty obvious, right? Does it pass the horizontal line test? Yeah, it certainly does, right? This is a one-to-one function, which is why I was able to write down g of x, which is its inverse function. What's the graph of g inverse look like? It's the cube root function, right? Shifted 2 to the what? 2 to the right, right? And I'll draw that one in blue. And check this out. So there was a y-intercept of 2 for the function. There's going to be an x-intercept of 2 for the inverse function, right? And so I'm not very good at these, but I'll try. So here's your y equal to the cube root of x minus 2, right? So this was f inverse of x, and the top one was f of x. So if I did the graph exactly right, the graph of the inverse function, it's going to be like the graph of the function turned on its side. That's kind of it, but to be more careful, the graph of the inverse function is obtained by taking every single point in the function's graph and flipping the x and the y coordinates. That's how you get from one to the other. You just take every point in the function graph and you take the x and the y and you flip them. I'll write this out more carefully, and I'll show you an example with this more detailed. But before we get to that, and also okay, let me shut up. Over here, what happened? Why didn't this work? Why are these not inverses? I mean, this is what you'd like to be the inverse, but the trouble was that if you look at the graph here, like when you pointed out in my initial inverse problem, that's a parabola. This one actually is a parabola, right? Here you go. This is your, oh man. Here you go. Here's your y equals, x squared plus 3, which is your f of x. And that, definitely not 1-to-1, right? What would happen if you just tried to take this graph and turn it on its side? You'd have a sideways parabola, right? That would fail the vertical line test. That ultimately is what we're up against here. If the function's invertible, it's got to be such that if you switch the roles of x and y and graph it that way, the resulting pattern has to pass the vertical line test. So if you think through this, what that means is the original function has to pass the horizontal line test. Because if you flip x and y, what was horizontal becomes vertical, and what was vertical becomes horizontal. But more on that in a minute here. So not invertible because it's not 1-to-1. How could you make this? How could you modify example 6 to make this function 1-to-1? How could we modify example 6? Let me do it in a different color. I'll do it in the most hideous shade of blue possible. It's known as Carolina blue. I have this marker. I'm not proud of it, but I have it. I went to NC State if you want to understand this joke. But anyway, so what if we just add some terms and conditions here, say for x greater than or equal to 0, right? In other words, if I set the domain of f equal to 0 to infinity, right? Then all of a sudden, I don't have the full parabola, right? I just have what? Instead of having the full parabola, I just have this guy, right? By fiat, I have eliminated the negative part of it, yeah? Now it passes the horizontal line test, right? And what else? This calculation's fine. And this calculation's also fine. But there's an extra step, right? But x is greater than or equal to 0 by assumption. Because we look at x in the domain of f for this calculation. So at the last step, hooray, x, which shows that f and g are inverse functions. What's the graph of f look like here? What's the graph of this square root of x minus 3 look like? I'll do it in red. It's, instead of having a, this one has a y-intercept of 3. This guy has an x-intercept of 3. And it's the same shape, but it's turned this way. Starting to see the graph of the function versus the graph of the inverse function, same shape, but turned on its side. So I think the 1-to-1 property in and of itself is maybe not that super interesting. To me, what's interesting is the idea of an inverse function. Because ultimately what we're going to see is that knowing inverse functions allows us to kind of undo equations. All right, so later when you take pre-calculus, some of you, what you'll see there is that we have trigonometric equations, and with just equations using sine and cosine and such. And those, if you have inverse sine, inverse cosine, inverse tangent, you can undo those equations and solve for something, right? Soon we'll have exponential equations, right? And we'll learn that we can take a logarithm of an exponential equation and undo the exponentials, right? This is where we're getting to. So to me, inverse function is in part just a means to an end of solving particular kinds of equations. And you've already seen the first example of this, which is when we have a square, the inverse function is the square root. But that comes with terms and conditions, right? You need things to be positive for that to actually work out. in contrast, the cube root is a genuine inverse to the cube. If you've got a cubic equation, you can take the cube root of both sides and solve it. You don't get all the solutions necessarily, but you get at least one of them, you know? I do think you get all the real solutions typically. But, okay, let's go on here. So there's a theorem, a couple of theorems I have to share with you. I'm going to stick with the graphical one to start with here. Theorem, which is just this. If A comma B is in graph of f, then B comma A is in graph of f inverse. So what this means is we can make a graph of a function. If we have a graph of a function, we can make the graph of the inverse function using this principle. I don't prove too many things in here, but I have proved this for all the other sections, and I should prove it for you guys too. There's really not much to it. What does it mean for A to B be in the graph of f? This means that B, right, is equal to f of A. That's what that means. All right? And what happens if you take f inverse of this equation? This gives us f inverse of B equals to f inverse of f of A. So this is what I was just talking about. You can take an equation and you can take the inverse function to both sides. And that is simplifying in some sense, because how does the inverse function work? Well, the inverse function and the function, what happens when they meet each other is they just kind of go poof and smoke, right? So like this equals A. That was the definition. See over here? Whenever f and f inverse are composed, they just undo each other. All right. But what I just wrote here, A is equal to f inverse of B. I'll write it the other way. This is exactly what we mean when we say that, you know, B comma A is in the graph of f inverse. That's what it means to be in the graph of f inverse. It means the input B gives you the output A. So the role of A and B is swapped for the inverse function versus the function. Right? And a follow-up to this theorem, I'm just going to make you a sort of schematic breakdown of how things go here. Real kind of sketchy comment, if you will, but it's true nonetheless. And so here we go. On the one side you have f, on the other side you have f inverse. All right, and we can make a little table. And here's how it goes. If you've got a horizontal asymptote over here, you get a corresponding vertical asymptote over there. If you've got a vertical asymptote over here, you got a horizontal asymptote over there. If you have a x-intercept over here, it gives you a y-intercept over there. If you have a y-intercept over here, you get an x-intercept over there. And it's more than just that. It's that this dictionary between the graph of the function and the graph of the inverse function, it's also like logical in the sense that the way you make the transition from one column to the other is you just switch the roles of x and y in the defining data for these things. Like, let me put it into practice for an example, yeah? So, example 7. So we could come up against something like, let's see here. Like this, all right? So maybe this point here is at 1. So that function's invertible, right? It passes the horizontal line test. What's the graph of the inverse? Graph the inverse function. This is given, now graph the inverse. Can you do it? So there's a horizontal asymptote for the red one, right? this has y equals to 0 as x goes to minus infinity, right? Oh, hey, Iona. Yeah. So this has this horizontal asymptote over there, right? That becomes a vertical asymptote over here, and this one, so this one, to be more careful, is what? It's 0, 1, right? That corresponds on the graph of the inverse to 1, 0. This y-intercept becomes this x-intercept for the inverse function. This horizontal asymptote becomes a vertical asymptote. But you see the nature of it? It's just this, this is x equals to 0 as y goes to minus infinity. That describes this vertical asymptote. It goes down, down, down. And then you have this guy over here like that. Something else I haven't said yet, but I really should have by now, which is that another way to see these two graphs is they're reflections of one another across the line y equals x. So you can say, going from here to here, reflect across line y equals to x. And that, those are flowery words for this following idea. If I draw the line y equals x right here, right? I'll make it dotted. This is not part of either graph. But to say that they're reflected across the line y equals x, what that means technically is that if you were to draw a perpendicular bisector to the line y equals x, right? And you were to measure distances, like from here, here's a perpendicular bisector. See, it's perpendicular to the green line. If I did my graph exactly right, if it was true, if it was faithful to the reflection principle, then this distance, d1, and this distance, d2, they would be equal. All right, so my graph is only as good as those are actually equal. When those are not equal, I only graph so well, okay? Any questions? Here, let me show you an example which typically appears on the next test. So here I give you a graph without a function, all right? So here's I'm going to give you a, you're just getting the graph by a picture, okay? So here's the picture. And let's see here, I'll start us out with, I don't know, let's say, that would be something like -4, -2, all right? And then I'm going to go to, let's say here, which maybe would be, let's see if I did it right. That point might be, say, -2, 2, all right? And then I'll go like, let's see here. Up here to 8, 4, all right? So this, and I'm going to connect these dots, okay? Okay, so this is your given y equals f of x as pictured, okay? Then the whole problem, all right, this is what appears on the test, right? Then the question is, graph the inverse function given this graph. How would you do it? So I'm going to put the solution now in blue, okay? So I may regret writing where I just wrote. Oh well, let me write it over here. Graph y equals f inverse of x. How do you do it? And I'm going to have to erase that. I can see what's coming here for me. So how do we do it, guys? You're like, it's 8:15 in the morning. It's been two years since I did algebra. I don't know. Leave me alone. Let me be. The phrase "let me be" is special to me. Did I ever tell you the story of "let me be"? I don't think so. My friend Crazy Paul, and he's called Crazy Paul for a reason. This is a story of his youth. He was about 10 years old. I think his mom worked as a nurse at a nursing home, and she took him to work one day. And there was a guy, and he was in a wheelchair. But worse yet, he was chained to the wheelchair. They had him in shackles. See, Paul didn't know that the man had Alzheimer's and he was trying to escape, as they will do sometimes, right? And so the guy says, Paul, 10-year-old Paul, come over here. He says, hey, boy, let me out of these chains. They got me stuck in here. And Paul, being a nice 10-year-old, undoes his whatever buckle so he can get out. And so at that point, the orderlies notice what's going on, and they come and they just forcibly like pull Paul away and just drag him away. And as they're hauling Paul away from the wheelchair, the old man sitting in the chair going, "Let the boy be! Let the boy be!" So that's whenever I think of "Let It Be," I always think of that. But anyway, well, I thought it was funny. It's funny when Paul tells it. So let's see here. So to find the graph of the inverse function, we just use this theorem, okay? You just turn the points around. So like minus 4, 2 gives you the point minus 2, minus 4. So it's like, instead of going this down and that much over, we go that much down and that much over. So it's like, I think my graph's not quite right to scale, but it's like down here, okay? So minus 2, so it's still in quadrant 3, minus 4, just flip the coordinates, right? This one, minus 2, 2, flips to 2, minus 2. That's like here. So I'm not changing the x and y, I'm just flipping them. And then 8, 4 changes to 4, 8. So that would be like up here-ish, right? And so the graph of the inverse function is, roughly speaking, something like this. And if I did the graph right, you should be able to see that it's a reflection across the line y equals x, and so that should be, if I did it right, this point should be the place where they both cross as they cross the line y equals x. Okay? So one way we can find the graph of a function, an inverse function, is graphically, right? But oftentimes we'd rather take an algebraic approach, all right? So let's talk about how to find the formula for an inverse function, yeah? So I would say it's a 4-step process, all right? So here's the process. How to find formula for the inverse function. All right, step number 1. It's a small step, but it's an important step. Write y equals to f of x. Step number 2. All right. Step number 2 is solve for x. Step number 2, solve for x. And I'm going to say solve for x equals stuff and y, all right? Step number 3, write f inverse of y equals that stuff in y, whatever it was from step 3, right? And step 4, if needed, swap y and x and write f inverse of x is equal to the stuff, but in terms of x instead. So example 9, see, we could have this. We could have x equals degrees Fahrenheit, and we could have y equals degrees Celsius, right? What's the relation between Fahrenheit and Celsius? Well, we could write it this way, right? Y is equal to 5/9 times x minus 32. That's the formula that relates Fahrenheit to Celsius. You can try it out. X equals to 32 gives you freezing. So 32 Fahrenheit gives you 0 Celsius, right? Try boiling. Boiling is 212 degrees. 212 minus 32 is 180. 180 over 9 is 20. 20 times 5 is 100. 100 degrees Celsius is boiling by construction, right? 212 degrees Fahrenheit is boiling by, that's where it ends up. Okay, so anyway, yeah, so this is the formula. Solve for x. What is this? We get 9/5 y equals to x minus 32. So that gives us x is equal to 9/5 y plus 32. That's the inverse relation. See, if I introduce function notation here, I'm saying this is my f of x, all right? And this down here is really f inverse of y. Now, you understand that I've broken one of the cardinal rules of college algebra here. I just wrote a function of something other than x, which is something I may have nonchalantly told you we'd never do in here earlier on. I lied. Sorry. I try not to lie. You know. But there's a reason that we want to talk about a function of something other than x here because of the real-world application, right? Because if you're using x for both degrees Fahrenheit and degrees Celsius in the same breath, it's confusing. It's nice to use x for degrees Fahrenheit and y for degrees Celsius. That way, in your application of the formula, there's no danger of confusing, right? Now, if you make a graph which has both f of x and f inverse of x on the same graph, and you insist on still using the same interpretation for this example, then you have x meaning two different things on that graph. It means degrees Fahrenheit for the function. It means degrees Celsius for the inverse function. And if you're not aware of this and you try to look at the graph and understand it, it will be really confusing, right? But anyway, that is part of the reason. So you guys have been taught, I'm sure of it, in your previous courses, at the start, you what? At the very beginning, you do what? You switch x and y, right? Everybody teaches this in like pre-algebra, like in high school algebra, pretty much. Other classes have told me this. You guys are, I will not play poker with you guys. Partly because I don't know the rules of poker, but also because I have no idea what you're thinking. But a lot of people say switch x and y at the start, right? The reason they do that is so that at no point do they find themselves writing f inverse of y. Oh no, a function of y, we can't do that, right? And understandably so, right? Because every graph did I graph function of y anywhere here? No, what did I do? I looked at the graph of the inverse function of x, right? Every one of these has been a graph of f inverse of x. So to do the graphing that I've been doing, to all of the graphical comments I've been making, they are with respect to graphing the inverse function of x on an xy plane, all right? That's true. But if you're interested in the formula in terms of y, it's much simpler. You just take the formula and solve for x. It's just that.